Hello guys, welcome back to the Foolish Engineer YouTube channel. Today we are diving into the world of inverting amplifiers. Well, it is the first application which we see whenever we learn about the op-amps. It may sound boring and has limited applications, but it's worth learning. So, let's start. Picture this. We have an input voltage of 5 volts, but we want to amplify it using the op-amps and get minus 10 volts as the output. This sounds a bit unrealistic, right? Well, not really. We just need an inverting amplifier. It represents the inverting output logic of this amplifier. It's like flipping the voltage upside down. But here's the catch. This circuit needs a negative voltage supply, or we engineers call it VEE, to get this output. Now you might be thinking, what's the use of the amplifier that flips a good positive signal? Well, inverting amplifiers have some pretty good applications. They act as phase shifters, help with the mathematical functions like integration, and even serve as mixers in the radio frequencies. Let's see how we can design an inverting amplifier. Imagine we have a sine wave signal of 7 volts to minus 7 volts with frequency of 3 kHz. Our goal is to amplify it up to plus or minus 14 volts with the same frequency. That means we need a gain of minus 2 volts per volt. Now, this is what an inverting amplifier looks like. I'm using the OpAmp TLV170 from TI as an example here. It needs a negative feedback. That means we give some chunk of output signal to the inverting terminal of the op-amp through a resistor. And we provide our signal to the same inverting terminal through a resistor. The non-inverting terminal should be grounded. Let's start with the component selection. First, we need to determine the value of the R1. The value of this resistor should be selected considering the output impedance of the signal source. The value of this resistor should be larger than the source impedance, but not too large, or else it can degrade the phase margin of the circuit and add additional noise. So we need to know the impedance of the source. Let's say the source impedance is 100 ohms. We'll choose R1 as 10 kilo ohms. Next up, we calculate the value of the R2 using this formula. In our case, it turns out to be 20 kilo ohms. Now let's find out if our amplifier can handle 3 kHz signal or not. Let's consider the non-inverting gain and gain bandwidth product, which is mentioned in the OpAmp datasheet. From these parameters, we can calculate the bandwidth of this OpAmp for this application, which is 400 kHz. But now, to avoid stability issues, we have to see the zero set by these passive components like gain setting resistors and input capacitance of the op-amp, which is greater than the bandwidth of the circuit. This can be calculated by this formula. And this value is 43.7 MHz, which is greater than 400 kHz. These capacitors are common mode and differential input capacitance of TLV170. These values can be obtained in the datasheet. Last but not least, we need to calculate the maximum slew rate required for this application. It's like checking if our amplifier can keep up with the pace, which can be calculated by this formula, where Vp is the maximum output voltage. So, this will be 0.26 volt per microseconds. Luckily for us, this op-amp has a slew rate of 0.4 volts per microseconds, which is more than enough for our needs. Now, we'll see the simulation of the circuit. I'm using Tina TI software to showcase the simulation. This is TLV170 op-amp IC. The R1 and R2, the circuit is same as we calculated. We are providing the plus and minus 15 volts as VCC and VEE. Our input voltage is a sine wave with 7 volts peak to peak, and the output voltage swing is beautifully between minus 14 volts to 15 volts. As you can see, when we have a positive sine wave, it is amplifying up to minus 14 volt sine wave, and its phase is shifted to 180-degree. And that's a wrap. I hope you picked up something useful from this video. The reference of this design is added in the description below. While checking the reference, don't forget to hit that subscribe button. It's right over there. I'll see you next time. Till then, stay hungry, stay foolish.